Good evening, everyone. My name is Amanda Everts. I'm the Executive Secretary with the United Suffolk Sheep Association. I'd like to welcome you to our Suffolk U webinar series. Tonight, Dr. Andrew Weaver will be discussing understanding parasite susceptibility and resistance. Dr. Andrew Weaver is the Assistant Professor and Extension Specialist for Small Ruminants at North Carolina State University. He received his Bachelor's of Science degree in Animal Science from Michigan State, where he also worked on the MSU sheep farm. He received his master's degree from Virginia Tech and completed his PhD with research in parasite resistance at West Virginia University. We are going to allow questions here at the end. So if you have questions, you can sure type them into the chat box. And those questions I'll feed those to Dr. Weaver at the end of the presentation. If you're watching live on Facebook, go ahead and comment in the comment section, and I will share those questions with Andrew at the end as well. If you would like to come back and review the presentation, it will be archived on our Facebook page as well as the suffolks.org website tomorrow. Again, thank you everyone for participating tonight, and thank you, Dr. Weaver, for sharing your information with us. And with that, I'll let you take it from there.
Sounds good. Thank you for the introduction, and I'm glad to be here tonight. Hopefully we can pass along some good information and keep this topic fairly understandable. So feel free to ask questions, and I'll get to those at the end. There we go. So Amanda gave a nice introduction there, so I'll just skip over this and get right into the topic here. So our parasite challenges, our parasitism in small ruminants is expanding. Traditionally, the Southeast U.S. has kind of been the hotspot for parasites, and where a lot of the initial selection was needed to make sheep more resistant. But that I think is shifting, and we're hearing now more reports of parasite issues in West Texas, California, Montana, areas that we've traditionally thought are too dry or too temperate to really see a huge parasite burden. And now we're starting to see more of those issues. So I think it's a problem that's expanding, and more people across the country, no matter where you live, may be posed with some of these parasite threats. In general, the parasites that we're most concerned about in small ruminants fall in this strongylid category. These strongylid nematodes, these include Homunculus contortus, Telardrossagia, Cuperia, and Nematoderius. But really, what we're focused on most and what poses the greatest threat here in the United States and really all over the world is Homunculus contortus. We also have some issues with the protozoan parasite Coccidia. But for tonight's presentation, we're just going to focus on these strongylid nematodes, specifically Homunculus. So Homunculus contortus, its common name is the barber pole worm, is a blood feeder. And you can see in this upper right picture, it's got this feature on its head called the lancet. It's a little tooth, and it slashes at the wall of the abomasum and causes blood release. And then when that blood is released, it sucks up that blood and feeds on the blood, giving it the female worm, the stereotype, that classic image of that barber pole appearance that you can see in the bottom image, where the blood-filled intestines wrap around the reproductive tract, and it gives it that barber pole appearance. This worm is highly prolific. It can release thousands of eggs in a given day. And in our sheep and our goats, we see anemia as a classic symptom of Homunculus infections, decreased performance, and then death in severely infected individuals. This parasite accounts for millions of dollars in economic losses annually, both from decreased performance as well as the death and the loss of sheep. So I think it's really important to understand the life cycle of Homunculus, to understand how we can manage the parasite and select for sheep that are more resistant to the parasite. So Homunculus follows a direct life cycle. The adult worms live in the abomasum, which is the fourth compartment of the ruminant stomach. They release eggs, and those eggs are deposited in the feces out into the environment. Those eggs then hatch into the L1 larval stage, And it goes through several molts until it reaches the L3 or the infective stage. That period in the environment from hatching to the L3 stage can take anywhere from 7 to 14 days. That's very dependent on the environment, the climatic conditions, and really hot, humid conditions that can be faster than that. And in colder, more temperate climates, cooler conditions that can be longer. So that time period is fairly variable. Once they reach the L3 stage, those larvae reside in dew droplets on the grass, on the forages. And they actually ride the dew droplets up and down the grass throughout the course of the day. So as the dew comes up in the evening and overnight, those larvae are up near the top of the forage, ready to be consumed, which conveniently coincides with when livestock are typically grazing. And then during the heat of the day, when that dew resides, those larvae migrate back down in those droplets near the base of the forage, where they can be protected from the sun and dehydration. So it's a pretty convenient system for the parasite and poses a threat for our sheep. And once those larvae, those L3, are consumed, they molt again to the L4 stage and then develop into adults. Now that time from the larval ingestion to mature adults that are producing eggs is generally around 21 days. That's referred as the pre-patent period. So typically from the time that the larvae are consumed until the time we get eggs in the feces is about 3 weeks. And here you can see some adult homuncus swimming around on the epithelial surface of the abomasum. So those worms, they swim. They don't actually bind, attach to the surface of the abomasum, which is really important to keep in mind. Those worms have to continue to swim to maintain their position in the gut. If anything stops them from swimming, they're flushed out of the gut with the rest of the contents. So they must continue swimming. They must continue moving to stay in the stomach. And we've seen this rise in dewormer resistance or anthelmintic resistance. So these worms go through sexual reproduction. Like I said, they're highly prolific, and female worms can actually mate with multiple males. So you get a lot of genetic diversity. And within any parasite worm population, we have some individuals which are resistant to the dewormer and some which are susceptible. Now, when we treat with the dewormer, we're wiping out those susceptible worms. And all that's left are those resistant worms to breed and generate the next generation of worms. So every time we use a dewormer, every time we treat a sheep, we're actually selecting for those more resistant worms. So we need to be very judicious in our anthelmintic use, and wise in our decisions to minimize the selection for worms that are more resistant. Right now we have, in many operations, in many settings, we have worms that are resistant to all 3 classes of dewormers that we have available. So really we need to look for alternatives and how we can evaluate parasitism and how we can manage those parasites in the face of this anthelmintic resistance. So the best way to assess parasite burden is through fecal egg counts. Fecal egg counts are simply a measure of the number of strongylid parasite eggs in 1 gram of fecal matter. Now you can't distinguish between the strongylid parasites by their egg stage. You actually have to wait for them to hatch and reach the infective larval stage before you can differentiate between the different strongylid parasites. So we simply label it as a strongylid fecal egg count. I put on here some really broad ranges on levels of infection. These are highly variable and dependent on the sheep and the operation and the environment and how resistant your sheep are. So in general, less than 500 eggs per gram, we're really not worried about it. Somewhere between 500 and 1,500 eggs per gram, those sheep are starting to get more infected and something you want to pay attention to. And above 1,500 eggs per gram, those sheep typically need to be washed a little bit closer, may need to be dewormed. The level of infection is certainly increasing. But like I said, those are pretty broad ranges. It would be great to be able to evaluate the adult worm burden, get a specific number of adult worms in a given sheep. That would tell us truly which ones are resistant, which ones aren't. But that's not very practical, as you have to remove the abomasum to be able to do that. It's kind of like taking carcass data on individuals that we'd like to use as breeding stock. It's just not very practical. So fecal egg counts provide a great alternative. So a lot of times this resistance versus resilience, the terms are interchanged, or one is used instead of the other. And I think it's really important to be able to differentiate them and know what one means versus the other. So resistance is that ability of the sheep to eliminate the parasite infection, actually get rid of the worms, eliminate that infection. That's optimal. That's really what we're shooting for. The ideal situation would be sheep that can eliminate that infection, target those worms, and not get infected. Resilience is more of the ability of the sheep to continue to perform despite some level of infection. The problem with resilience is sheep tend to get to a breaking point. Something happens, there's a stressor like weaning, for example, and those sheep break. You don't know exactly when it's going to happen, and when it does happen, it can cause sheep can get severely infected, die. You can lose some individuals, and if we can't predict that time point, you're kind of sitting on a volcano that's ready to erupt, and you don't know when it's going to happen, and it's hard to manage. FAMACHA scoring is a great on-farm tool to evaluate the level of anemia. So you're looking at the color of the membranes in the eye to evaluate the level of anemia. Sheep that are more anemic, you would assume have a greater homunculus infection because they consume that blood, but it doesn't tell us the exact level of infection, and it's more subjective compared to fecal egg counts. So really, we want to focus on this resistance. And there's variation in parasite resistance both within breed and between breeds. So we have breeds that we designate or we could classify as parasite resistant, like some of our hair breeds like the St. Croix, Barbados Blackbelly, where we have all other breeds that are more susceptible. The Suffolk has been a breed that breeds. So that's really important to keep in mind and understand for selection. So in terms of our selection tools, traditionally we've done phenotypic selection. It's just measuring phenotypes, whether that be fecal egg counts or other performance measures, and selecting individuals that have those better phenotypic traits. But we have much more powerful tools than that now. And we have tools that we can select much more accurately with. And those would be estimated breeding values. And we can use those for quantitative selection. So those EBVs are a measure of individual genetic merit for a given trait. And it combines that individual performance along with pedigree information like sire and dam performance, grandsire, granddam information, all their progeny data. So you get a much bigger, much clearer picture of what the true genetic merit is of that individual for a given trait. And the accuracy is so much higher. It's a much better tool to use for selection. And it's also really important to remember that you can't select for what you don't measure. So I think anything that we want to start paying attention to, we want to put emphasis on, you can't do it, you can't make any progress unless you start measuring it. So the first step is to start measuring the trait. So we have these genotypes, and we have this genetic makeup that we can predict based on their breeding values or their breeds. And we have a phenotype, whether that be parasite resistant or parasite susceptible. But what's causing that genotype to result in that phenotype? What's the intermediate that's causing that phenotype to be expressed, whether the sheep are able to be resistant and prevent that infection, or whether they're susceptible and succumb to the parasites? And that would be that immune response. So the cellular, the antibody response, and whether that sheep is able to have an immune system that can recognize and respond to that parasite infection. So what is true parasite resistance? So the St. Croix is a great model for what true parasite resistance is. And in some of the graphs on the following slides, they're going to be designated as hair. So we can raise sheep in a naive environment. So these sheep have never seen a parasite before, homunculus before, And then we give them what's called a primary infection. So we artificially dose them with larvae. They've never seen the worm before. This is their first response to it. And even the St. Croix that we would describe as parasite resistant do get a fecal egg count. But by 5 weeks post-infection, they're able to clear that infection on their own and maintain a 0 fecal egg count. Whereas we think our more susceptible breeds, like the Suffolk, which are going to be designated as the wool, you give them that primary infection and they get a much greater infection, and they aren't able to clear that infection on their own. Then we go ahead and we deworm those sheep. We clear that infection for them. We let them rest for a couple weeks. We go ahead and give them a second infection, which is called their challenge infection. And during the challenge infection, those hair sheep never get infected. They maintain a fecal egg count of 0 for the entire infection period. Where the Suffolk sheep, our wool sheep, get a challenge infection. They get a rise in fecal egg count. It's not as great, it's not as high a magnitude as our primary infection, but they do still get infected. So that ability to truly clear that infection and prevent that infection is what we would define as our true ideal parasite resistant breed. So those larvae are ingested, and this graph depicts total worm burden in days after infection. So you can see by day 7 post-infection, those wool sheep have a greater worm burden than our hair breeds. So fairly soon after infection, we start to see some differences between our types in terms of level of infection. So what's causing that? Why are these wool breeds getting infected and these hair breeds really not so much? And it really has to do with that immune response and how those sheep are able to respond to that infection, recognize and respond to that infection. So this shows our immune cell response. And you can see in our hair sheep, by day 3 post-infection, they have the same cell concentration as what our wool sheep have at day 7 post-infection. So it's taking our wool sheep 4 additional days to reach the same level of cell concentration at that site of infection than our hair sheep. So those hair sheep are able to respond earlier and at a higher magnitude than our wool sheep are able to. And that delayed response in our parasite susceptible sheep allows time for larval establishment. They aren't able to recognize it as fast, they aren't able to respond as fast, and as a result, those larvae have time to get established, get comfortable in the gut. So what are those cells doing? So those cells are actually able to release their DNA and form these structures called nets or extracellular traps. So those green lines are actually their stained DNA. So they're able to release their DNA, the DNA bind up the larvae and prevent them from moving. It holds them tight. And remember what I said earlier, if the worms aren't able to swim and maintain their position, they're washed out of the gut. So these cells are binding up the larvae and preventing their movement. This is a little bit closer image, electron microscopy of these immune cells bound to the surface of a larvae. So I thought this is a cool picture. Came out of Dr. Bowdridge's lab and really shows those cells bound to the surface of that larvae. So what are those cells doing in addition to just binding up the larvae? They're also decreasing the larval energy. So ATP is a measure of energy, and lower ATP in our larvae indicate greater larval death, less larval energy. And so in our parasite-resistant breeds, we see the ATP concentration is lower than that in our parasite-susceptible breeds. So those cells in our parasite-resistant breeds are able to reduce the larval energy when compared to our parasite-susceptible breeds. So they're impacting larval survival as well. And then they're able to generate, these hair sheep are able to generate this Th2 type immune polarization. So this Th2 type response is often associated with parasite infections as well as allergic reactions. And it's commonly referred to as the weep and sweep response. So we get an increase in mucus production and increase in gut contractility. So essentially you're washing out whatever's in the gut and you're increasing smooth muscle contractions, which is forcing whatever's in the gut out. And so the idea is you're flushing out the worms. Those worms, anything that's in there, it's a less favorable environment for them to be hanging out in. So to summarize all this, I know some of this immunology stuff can get pretty deep. So this is, I think, a nice summary of the last few slides that we talked about. Those larvae enter the gut and they cause epithelial damage. That damage results in a signaling cascade, and we get that the cell and humoral response, the Th2 polarization, that weep and sweep response, and we get larval expulsion that results from their inability to swim to maintain their position, as well as an unfavorable environment in their gut for them to be there. Those larvae are bound up and washed out. So they're not able to stay in the gut, they get washed out. We have true parasite resistance because we don't get larval establishment, we don't have an adult worm burden, we don't have a fecal egg count. So that is the ideal situation. But I think what is more relevant for all you folks that are probably looking at producing purebred animals, purebred breeders, and crossbreeding is not very practical as a means to insert some parasite resistant genetics. So we need to look at within breed variability and within breed selection for parasite resistance. So many traits can be described on this normal curve, this normal distribution. And so we have most of the individuals within a breed or flock that exist around breed average. We have some individuals that are extremely low in their breeding values and other individuals that are extremely high. In the case of fecal egg counts or measuring parasite resistance, we want to reduce fecal egg count. Lower fecal egg counts mean greater parasite resistance. So if we select for those individuals which have a more extreme negative fecal egg count breeding value, we should be able to reduce the fecal egg count in our flock, improve parasite resistance. So it's important to remember that the phenotype is a combination of genetics and environment. So we have genetics as well as the environmental factors, whether those sheep are housed in a confinement operation, whether they're housed out on pasture, how much supplementation they receive. All that's going to impact that phenotype that we observe, whether those sheep are more resistant or more susceptible. So there's multiple ways to manage parasites. Today we're going to focus on the genetic side. And if we think about how do we make genetic progress or what goes into genetic change, we have the heritability, selection intensity, the phenotypic variation, and that divided by the generation interval. So traits that have greater heritability and more phenotypic variation, there's more opportunity for genetic progress, for genetic change. And the good thing is, even within breeds that are traditionally labeled as parasite susceptible, we still have quite a bit of phenotypic variation. So there's quite a bit of opportunity for selection. Fecal egg count is not normally distributed. So in general, it follows a 70-30 rule. So 70% of our worms are carried by 30% of our sheep. So this below this graph here is a distribution of just the raw fecal egg counts from the Virginia Tech Suffolk flock in 2018. Those fecal egg counts range from 0 to about 3,500 eggs per gram. You can see a majority of the sheep have fecal egg counts between 0 and 500. Majority of the sheep will have what we consider just a low infection. But there's also individuals that are quite a bit more infected. So there's quite a range there. And there's opportunities to select within that population. So like I alluded to earlier, we have this fecal egg count estimated breeding value. The breeding value was developed by Dr. Notter in his lab at Virginia Tech in the early 2000s. The fecal egg count heritability generally ranges from 20 to 25%. It's considered moderately heritable, so it'd be similar to your growth traits. And it's reported as a percent change. So negative values are good. So for example, if we have a negative 100 fecal egg count EBV, that would be a 100% reduction in fecal egg count, as opposed to a positive 100 fecal egg count EBV, which would be a 100% increase in fecal egg count. So for example, we have these two individuals. One has a fecal egg count EBV of -60. The other has the fecal egg count EBV of -10. Now, an individual passes half of their genetic information to their progeny. So you have to take that EBV and divide it by 2 to get the progeny difference, the expected progeny difference. And so for the top ram, his progeny, we'd estimate, expect their progeny to be around -30%, where the bottom ram would be around -5%. So in the progeny, the expected difference in fecal egg count between progeny of these two rams would be somewhere around 25%. So this is the Katahdin fecal egg count or fecal egg count EBV percentile report. And you can see those elite individuals within the breed are sitting right there at -100, 100% reduction in fecal egg count. And that range goes all the way up to upwards of 1,000%. So 1,000% increase in fecal egg count and those individuals that are the poorest for parasite resistance within that breed. The average sits right there between -30 and -50, depending on whether you're looking at weaning or post-weaning fecal egg count. So the Katahdin breed has made some progress in fecal egg count. You can see over the last 10 years or so, they've identified this as a trait that the breed considers important and a trait that many of the breeders want to select for and improve. And they've been able to make progress, and that progress has continued. And so it certainly can be done. It just takes measuring and a little bit of selection emphasis. So to validate those fecal egg count EBVs and look further at this trait, this was some of my PhD work. We took rams with extremely low fecal egg count EBVs and rams with extremely high fecal egg count EBVs, and randomly mated those to a Katahdin ewe flock down in Southwest Virginia. So these are their post-weaning fecal egg count EBVs. On the low side, they ranged anywhere from -100, -68, with an average around -85%. On the high side, we had sires upwards of 500 for their post-weaning fecal egg count, an average of 288%. So randomly mated these to a group of ewes, evaluated those progeny, took fecal egg counts every 2 weeks over the course of their first 4 months of life or so, and selection works. We were able to observe what we thought was going to happen. Those progeny born out of low fecal egg count sires had lower fecal egg counts than the progeny born out of high fecal egg count sires. So this is just proof that the EBV works. The fecal egg count EBV is valid. Selection works, and progress can be made. But along with this, kind of another question came to mind during the course of this project. And if you remember back talking about that immune response and its association with parasite resistance or susceptibility. So if we have an enhanced immune response that's associated with increased parasite resistance or that lower fecal egg count, then does the fecal egg count EBV predict general immunity and lamb fitness? So does selection for lower fecal egg count through the fecal egg count EBV, does that enhance general immunity and improve lamb fitness to maybe more than just parasites, if we're improving the immune response? So this is death loss data from the 2 years of that project. So in year 1, those lambs sired by high fecal egg count rams had a death loss 3 times higher than those sired by low fecal egg count rams. In year 2, that difference wasn't nearly as significant, but in year 1, we had a pretty severe Clostridium perfringens type A outbreak, and we lost quite a few lambs from that. In year 2, we decided to go ahead and vaccinate for type A, and we saw those death losses decrease. But I think it's important to note that regardless of vaccination status, regardless of year, the death loss for the low fecal egg count sired lambs was generally 8 to 10%. So regardless of vaccination status, our death loss is fairly constant for low fecal egg count sired lambs. So if you select for low fecal egg count, you may be able to minimize your risk of having an outbreak like this and having severe death loss in lambs, because maybe those low fecal egg count lambs have a better immune response, are more fit when faced with a variety of different pathogens. This work is continuing, and Dr. Bowdridge's group up at WVU is continuing to work on this, and we've got another project actually going right now to further address this and look at some of those specific immune responses within these high and low selected sheep. But I think it's also important to look at what other industries are doing. Both on the dairy side as well as the beef side, we're seeing this push for disease-resistant genetics. On the dairy side, they've come out with what's called the Immunity Plus Index, and it's a measure of immune response, immune fitness, and it's been associated with resistance to a variety of different diseases. On the cattle side, the Angus Association earlier this year released an article with their intent on coming out with a similar index and trying to get some of that data collected and that established this summer. So these other industries, which I know have greater animal numbers, are pushing in this direction. And on the sheep side, fecal egg count might be a convenient tool that we've already been using, that we already understand fairly well, that we already have a breeding value for, that might be a predictor in a similar way of this general immunity and disease fitness. So I think it's something that might be worth pursuing, and that we can look into and see if we're seeing this general immunity associated with our parasite-resistant genetics as well. So what about its relationship to other traits? Does the fecal egg count, EBV, does selection for fecal egg count impact other traits? In terms of our weight traits, it's pretty minimal. And I think you can select for improved fecal egg count without having too much impact on your growth traits. We have, in the first column, we have our weaning fecal egg count, post-weaning fecal egg count. On the second column, you have that trait that it's compared to. So weaning fecal egg count compared to weaning weight, we have a mild genetic correlation, slightly negative there, but phenotypic correlation is really minimal and close to zero. In terms of post-weaning fecal egg count and post-weaning weight, both genetic and phenotypic correlations are pretty much zero. So you should be able to select for one without impacting the other two greatly. And our weaning fecal egg count and post-weaning fecal egg count are pretty highly related. You can expect sheep that do have a higher weaning fecal egg count to also have a greater post-weaning fecal egg count. And it's also something to keep in mind when if you're submitting data, if you submit data for weaning or post-weaning, we can get EBVs on the other trait just through that correlation. There is also an effect of birth and rear type on fecal egg count, on lamb fecal egg count. So those lambs that are born in multiple litters, either born twin or born triplet and raised that way, do tend to have greater fecal egg counts than our lambs born as singles and raised as singles. And generally, younger individuals have greater fecal egg counts than our older individuals. So this is dam age and dam postpartum fecal egg count, or otherwise known as the periparturient rise. So those yearling ewes, their periparturient rise, their rise in fecal egg count after lambing, is generally going to be greater than that of older individuals. In general, lamb fecal egg count rises with lamb age until about 120 to 130 days of age. Lambs typically, if they're in a grazing environment, they'll start grazing. Their rumen develops and starts working around 30 days of age. And so those animals start getting infected when they start grazing. And from that time period, it continues to grow until that animal either is able to respond to that infection and minimize that infection, or that infection continues to rise, that fecal egg count continues to rise, and you get lamb death, or at least you get severe reduction in lamb performance. So it reaches this kind of tipping point where the lamb has one of two options. They can either respond or they cannot. And those lambs that don't respond typically don't make it very long without some sort of intervention. So let's talk about measuring parasite resistance. Get to the the practical side and how can we start selecting for parasite resistance and measuring these fecal egg counts. So NSIP reports a weaning and post-weaning fecal egg count. So weaning corresponds with that time period when you take weaning weights, around 60 days of age. Post-weaning, you can do early post-weaning or normal post-weaning fecal egg count at 120 plus days of age. In general, you want to make sure you wait at least 30 days after you collect your first fecal egg count sample to collect your second. So you should have at least 30 days between that weaning and post-weaning sampling. In general, we'd like for the average fecal egg count for a contemporary group to exceed 500 eggs per gram. That gives us the most power in our analysis. If their fecal egg count average is less than 500 eggs per gram, it's a little bit harder to sort out some of those differences. So the key is, and there's been a lot of discussion about when we sample lambs and when's the best time to collect those fecal samples. There is some cost associated with that generally, and some time, and you'd hate to collect all your fecals then realize that they're all zero. And so I think a good time to do it is to monitor, use FOMACHA score as a method to evaluate the anemia, and use a subjective evaluation of the level of parasitism. And when you start getting those individuals with FOMACHA scores greater than or equal to 3, when you get to a point when some of those lambs are going to start needing treatment, needing to be dewormed, then that's a good sign that there's a level of infection in your lambs that when you collect a fecal, your average should be high enough, hopefully should be high enough. So you want to collect a fecal on all of your lambs and then deworm either those that need it or the entire group. Selective deworming breaks your contemporary group structure. So if you're going to only deworm those individuals with high FOMACHA scores, in later fecal egg count samples, it'd be best to put those in a different contemporary group or move them from the contemporary group because those individuals have gotten treated and they're likely to have a lower fecal egg count or could have a lower fecal egg count compared to individuals that have been able to make it without being dewormed. And so they're really a different contemporary group at that time with that treatment and needed to be treated as such. So you can either collect that fecal sample, deworm everything, and then restart that kind of 30-day time clock, or you can just selectively deworm those, keep track of those that you have dewormed, and manage those accordingly. In terms of parasite management, it's probably best to just selectively deworm, but if you really want the data and to keep that whole contemporary group together, then you need to treat all those individuals the same. That primary infection, that first infection, the data from that is generally less accurate than our challenge infection, that second infection. That challenge infection is generally more telling about the true level of parasite resistance that individual has. So the timing of fecal egg count collection is really important. And this is going to vary by region and where your parasite challenge is when it occurs during the year. Certainly here in the Southeast, it happens a little bit earlier than those of you that might be further up north. This is natural infection data from Katahdin sheep located in Southwest Virginia. So fecal egg count just slowly rises there before weaning. These are March-born lambs. So wean them out 60, 70 days in early June. And you can see after weaning for 2-3 weeks, the fecal egg counts really go all over the place and peak. And so this is from that same project I discussed earlier, where you have low fecal egg count sired lambs and high fecal egg count sired lambs. And actually for one sample collection there, our low fecal egg count lambs had a higher fecal egg count than the high fecal egg count sired lambs. So that stress associated with weaning can really affect what our fecal egg counts are. So it's best to collect a fecal egg count either at or before weaning, and then wait at least 3 weeks post-weaning to collect another sample. You can see starting at the end of June through early July, those fecal egg counts segregate like we would expect them to do based on the fecal egg count breeding value. So that time around weaning is really iffy and can be very highly variable on fecal egg count. So it's important to keep that in mind. And it's also important to remember the sheep need to be challenged. They need to be exposed to the parasite. we need to be able to see how those sheep respond when they're exposed. And after larval exposure, it generally takes about 3 weeks before you're even going to see a fecal egg count. So it's best to time our fecal collection for 4 to 5 weeks after we know that there's been parasite exposure. So to just go back to that life cycle again, and a brief overview of that portion of the life cycle that occurs within the sheep, we have our infective larval stage, those L3 larvae residing in the dew droplet on the grass. Those are consumed by the sheep. And in that first week, those L3 become L4 stage larvae, and they begin feeding. And that's really important to remember, that those L4s, those immature adults, are feeding. And so while we don't see a fecal egg count, we could be getting sheep that are more and more anemic. And sheep can actually die of what's called acute homuncosis before any fecal egg count is observed. And so it's really important to monitor those individuals. Even if you don't have a fecal egg count, they may still have worms in their gut and worms that are feeding. So between 14 to 21 days, 2 to 3 weeks post-infection, those larvae mature to the adult stage, reach maturity, and begin shedding eggs. And then we're really shooting for that period 4 to 5 weeks after infection to collect a fecal egg count, fecal sample. So how do we challenge sheep? Traditionally, and probably the best method is through natural infection. And that's infection resulting from consumption of larvae on the pastures while they're grazing. This is the most natural, what we consider our standard form of infection. It assumes that all lambs in the contemporary group have an equal opportunity for infection. So we're assuming they all have the same opportunity to get infected, but the actual level of intake is unknown. We don't know for sure if they're all getting the same level of larvae, if they're all consuming the same amount of infective larvae. But it's a better representation of their ability to handle parasite infections in the face of a lot of other environmental challenges. So sheep that are out grazing are exposed to heat stress, exposed to co-infection with other parasites, could be coccidia, other bacterial challenges, etc. They're faced with a lot out in the grazing environment. And using that natural infection model, we can really evaluate how well they're able to respond to the parasite in the face of all these other challenges as well. There's also artificial infection, which are most frequently used in experimental settings. We use them in a controlled environment. We can dose those lambs with a specific number of larvae. So all the sheep are getting the exact same number of larvae. We know the level of intake, and we can look at how those sheep respond to that infection in a more controlled setting. One issue we've had with this is you put these sheep, say, in a barn and give them this artificial infection. That improved plan of nutrition while they're in the barn, the less heat stress, they're frequently under fans, they're in a more comfortable environment, reduces a lot of those environmental challenges. And so that sheep can really just focus on managing that infection. And a lot of times we see a lower fecal egg count, lower parasite burden in this setting. But at the same time, we don't know exactly how many larvae they consumed in the natural environment. So it's the artificial infection method at this point is just used for those experimental settings. So I want to give just some background on a flock that has been doing fecal egg counts and has been generating fecal egg count breeding values for a number of years now. The Virginia Tech Suffolk flock and Dr. Greiner, they've been collecting fecal egg counts on their Suffolk lambs for a number of years now. Just give you some background on that flock and how it's managed. All the lambs are exposed to grass roughly 2 weeks post-lambing. So they don't have a whole lot of barn space at that facility, so they can't keep all the pairs inside. So once those sheep come out of the jug, they go into group pens, and once everyone's acclimated, they head out to paddocks outside the barn. So they're exposed to parasites pretty early in life. In early May, the rams are moved up to the ram test facility to be fed up there. And they are provided ad libitum feed access, full feed, but they do have access to pasture lots. So they can get some natural infection. And these sheep have actually been artificially infected in the past to really get a solid infection. Because like I said, when they're on full feed in a more comfortable environment, sometimes it's hard to get fecal egg counts high enough to get good counts for EBV generation. So they've gone ahead and infected those individuals for 4 to 5 weeks and bumped those fecal egg counts up to get those counts higher, to get a good data set on them. The EULAMs, their contemporaries, are developed on grass all summer. So we have individuals that are related, siblings here. One group is managed at the ram test, the other group is managed on grass, and they get a fecal egg count before any of those lambs need to be dewormed. So just looking at the fecal egg count EBVs on those individuals. Now, it's important to note there hasn't really been any selection pressure placed on fecal egg count at this point. They've been collecting the data and generating these breeding values. They haven't really placed any pressure on it. So you can see that green line is average post-weaning fecal egg count, and it's remained relatively constant for the last 10 years or so. But you can see the range, the high end of the range depicted by the red line, the low end of the range depicted by the blue line. There is some variation there. We have fecal egg counts at this point in that flock that are upwards of 100 to 150, and as low as around -50. So there's individuals that you can certainly select from, and if you wanted to make progress and improve fecal egg count, improve parasite resistance within the Suffolk flock there, certainly be possible. So I just wanted to show this as an example that even with a breed that we've traditionally labeled as parasite susceptible, there's still quite a bit of variation for fecal egg count, and there is opportunity for progress. So like I said, selection opportunities exist and they work. The breeding value does selection for fecal egg count breeding value. You can reduce fecal egg count, improve parasite resistance, and there's phenotypic variability even within a breed that we've labeled as parasite susceptible. So despite that label that's been traditionally assigned, there's certainly room for improvement and opportunity for improvement. There's the opportunity for selection is there. The sheep need to be challenged. They need to face that parasite burden. We need to get those fecal egg counts high enough that we get a meaningful data set. Progress may not be immediate. It may take some time, but you just need to trust the numbers, keep selection pressure there, and stick with it for a few years. Whether that progress is measured in their actual EBVs or if it's measured in the number of lambs that need to be dewormed or their Fibonacci scores, whatever it might be, it might take a little bit of time to realize some of those differences in, say, deworming frequency. But just give it some time, continue to select for it, and put some emphasis on it. And then selection for parasite resistance may result in tougher sheep, sheep that are resistant to more than just worms. And I think that's kind of the next step and where we're going in the future. There's certainly more work to be done in this. And I don't want to say it definitively does that, but I think we've seen some evidence and there's some opportunity potentially there. And we'll keep you updated as we get more of that data. I also wanted to pass along for those producers that are in an SIP or interested in doing fecal egg counts, the group at the University of Rhode Island is offering free fecal egg count analysis this summer for those individuals in an SIP that market to the Northeast or are located in the Northeast, and then those non-NSIP members that are living in the Northeast and are willing to generate some other data as well in terms of Fibonacci scores and et cetera. So this will all be included with the slide set. And so if you'd like any more information on this, that'll be included. The email is listed there for you to get in contact with those folks about fecal egg count analysis as well as NSIP membership. I'd also like to acknowledge Dr. Bowdridge's lab. I did my PhD with that group, and really they've led the way in a lot of this work. Most of those figures and the data that I showed came out of his lab. Dr. Garza, Javier Garza, and Denzel Middleton have done a lot of the work with neutrophils and some of that cellular response to parasite infection, and Dr. Shepard has done some of that cellular work as well and monocyte work, and they've really helped us better understand a lot of this, the immune mechanisms associated with parasite resistance. So I want to acknowledge them and all their efforts, and our collaboration with Virginia Tech has been really important in a lot of this work as well. So would not be possible without them. And I'm really appreciative of all they've done for my training, as well as our understanding of parasitism and immune response in sheep. And with that, I will take any questions.
All right, great. I do have some questions for anybody who's on Zoom or Facebook. If you're joining us via Zoom, please type your questions either in the chat window or question and answer. If you're on Facebook Live, go ahead and just put those in the comment section, and I will share those with Dr. Weaver. Okay, the first question is, what breed were those genetic and phenotypic correlations from? Don't the small phenotypic correlations between fecal egg count and growth traits depend on environment? I would think they would be expected to be higher or more negative the more challenging the environment.
Yeah, so all of this data is generated from catodons. So all of the relationship to other traits, this table here, as well as the birth and rear type data, the dam data, as well as the fecal egg count with lamb age, that's all catodon data. They probably have the most robust set of fecal egg count data, the largest data set in the National Sheep Improvement Program. And so a lot of this work has been done with them so far. So yeah, those phenotypic correlations, that environment can play a part with that, and certainly could influence, the catodon sheep. They've been, a lot of catodon producers place a lot of emphasis on fecal egg count and parasite resistance. They're raising sheep in largely a forage-based environment, and they're keeping growth in check. They're selecting for fecal egg count as much as they are for growth. So they're not really singling out one trait or another to really chase after. They're keeping that. They have to keep the sheep somewhat moderate in size to make sure that the ewes are sustainable on grass. And they're putting a lot of emphasis on fecal egg count. So that might have some to do with that phenotypic correlation being pretty minimal. Yeah, and environment could certainly play a role there in how we manage those sheep when they get infected, and the level of supplementation that they're getting during that infection.
All right, next question is, how can you do fecal egg count on hundreds of lambs in an efficient manner? All the individual testing works okay when you have 25 to 50 lambs or graduate students performing the test. But in West Texas, where we have large flocks, doing hundreds of fecal egg counts will take weeks of time. Any suggestions?
Yeah, and that's kind of the hard thing with fecal egg counts. It's a fairly inefficient process until you get some people helping. In a lab, you can run fecals pretty quick because you have 5-6 hands around to run samples. It's much more difficult when you're by yourself and you have hundreds to do. You can refrigerate your fecal samples. So those samples can stay refrigerated and they stay good for about 2 weeks. So you can really collect your fecals on one day, put them in a refrigerator, and then even if you can only handle 10 a day, which most people can run about 8 to 10 fecal samples an hour by themselves. So if you can do, say, 10 or 20 a day over the course of 2 weeks, then you can get through a fair number of them. That's probably the best advice for if you're by yourself. They are storable, so don't feel like you have to run them all in one day and sit down and do them all at one time. You can work through a few at a time over the period of a couple weeks.
On a follow-up to that topic, is there value in just testing the rams?
So I think any measurement is better than nothing. Anytime you can measure a trait and understand what's happening and the variation within that population, I think is good. So something is better than nothing. You're not going to have as wide of a viewpoint. You're not going to be able to put as much selection pressure or emphasis on it. You won't be able to select for, within your, you might get fecal head count EBVs on the use just through relatedness, but they're not going to be nearly as accurate. And so you might not be able to put as much pressure on the use side, but you can certainly use some of that to select your RAMs. And like we showed with some of that Katahdin data, just RAM selection alone, randomly mated to a U flock, you can make some progress. So I think something's better than nothing. And if all you're able to get done, say by yourself or in the time that you have, or the financial resources you have, is just do a smaller group, then that's, I think, better than nothing.
Okay, and there was a comment that said if you go to Wormex info website, the consortium has a list of places that you can do the fecal head counts for $5 per head, I'm guessing. So that's
yes, it's per head.
Comments.
So there are a few places that are offering that service. And so if you're interested and you don't want to do them yourself, you don't have time to do them yourself, West Virginia University, I believe Texas A&M are offering that service. Jim Miller's lab at LSU, I think, is as well too. So you can go to wormex.info and that information is listed there. So that price is, it might sound expensive. It's significantly cheaper than having your local veterinarian do it. Now that data can only be used for genetic evaluation, genetic selection purposes. It can't be used for diagnostics, but you will get the fecal head count data and you can use that for your EBVs.
What is the resistance heritability of the sires versus dams?
So the heritabilities, they've ranged as, I've seen the ranges as much from 10%, 10 to 15% to as high as 30 or 40%. In general, they're sitting around that low 20 point. So right around 20% for the genetic component of fecal head count.
Next question is, are you suggesting to sample both replacement ewes and rams?
Yes, that would be ideal. Ideal, you sample your entire lamb flock, the entire contemporary group, and then you can make selection decisions both on the ram side as well as the ewe side. Increase that selection intensity, and you should make more progress that way.
Next question is, does valbazen affect the cycle of breeding sheep?
So in general, our white dewormers have the greatest level of, our worm population has the greatest level of anthelmintic resistance too. So we frequently use prohibit levamisole to treat individuals. Generally, when one dewormer stops working, use them in combination. So give each dewormer at the given dose, the labeled dosage, but all at the same time. So I would be hesitant to use some of those the benzimidazole class dewormers alone. I'm just not sure that they're that effective. In terms of its effect on the breeding season, can't remember off the top of my head. I'll need to double check on that. But I can get you more information if you need that.
Okay. How can NSIP Suffolk breeders balance between full feeding for maximum post-weaning weight gains and challenging lambs enough to generate a meaningful fecal head count?
Yeah, so that's the hard question. You got to get rams that are big enough to sell and cover ewes in the fall as yearling or as buck lambs, but you still want to get some of this data. I think there has to be a little bit of a compromise in terms of getting those sheep infected. But we also need to remember you can really do the entire process and get fecal head counts within about a month, 4 to 5 week time period. So those sheep need to get infected, and then it takes about a month for that infection to get established and be able to collect fecals in a meaningful way. And so it's really only a month, and it could be less. They don't even need to be exposed to worms. If you're confident that they're going to get infected, they don't necessarily need to be exposed to worms for that long. They just need to be out, have the opportunity to get infected, consume some larvae, and then you could bring those sheep back in the barn and feed them and get a fecal 4 to 5 weeks after you turn those sheep out or after you brought them in. And you go about it that way. Now, that putting them back on feed might minimize how strong of an infection they get, but that can be tried if you want to, if you don't want to compromise too much on time on feed and growth.
All right. Is there any other questions? Just give everybody just a little bit here to see if anyone has anything else. I don't see anything coming in. Just thanks again, Andrew, for joining us tonight and sharing this information. For those who are joining us this evening, again, this will be archived on our Facebook page and also on suffolks.org. Andrew, is there any way that I can get a copy of the slides to post as a PDF as well?
Yeah, I'll send you those now.
Perfect. Okay. So yes, the slides will be available on suffolks.org website probably tomorrow afternoon. And if you have any questions, Andrew's information is on the last slide that you could certainly contact him with any questions you may have. So thanks again for joining us. Thank you to the Breed Improvement Committee for putting together and organizing this webinar. Thank you, Dr. Weaver, for joining us, and thank you for all the individuals who took some time tonight to learn more about this topic. Have a good evening.